last time we talked about how to find the strength of magnetic force on a moving charge moving through a magnetic field. We learned that, uh, let's go ahead and write that up there, that the magnetic force is equal to the absolute value of the charge times the velocity of that charge times the strength of the magnetic field. And then we also threw in times the sine of the angle the charge is moving relative to the magnetic field. So if your angle is 90, if you're moving perfectly perpendicular to it, sine of 90 is just 1. We really just kind of leave that part out there. All right, so today we're going to start talking about specifically what direction is that magnetic force. We know that it was perpendicular to both the direction the charge was moving and the magnetic field. So really to find this out, we're going to use what's called the right-hand rule. Um, uh, we're going to look at 3 different charges here. Charge 1, charge 2, and charge 3. Charge 1 is a positive charge, and we're going to say that all 3 charges are starting moving perfectly perpendicular to a uniform magnetic field. In this case, the magnetic field is coming out of the screen at us, and all of the charges are moving to the right. Okay, charge 1 is a positive charge. I guess particle 2 is not charged, so it's actually, not an ion. Uh, and then the third particle has a negative charge to it. So to figure out the direction, the way it's going to move, we're going to use the next right-hand rule, because you can't have enough of those. Um, really, this I'm going to call this one the magnetic force right-hand rule. Some places are going to number the right-hand rules, but I figured you can kind of address these from any angle. So really what the magnetic force right-hand rule says, I know my handwriting's horrible. We're going to use kind of an open hand, kind of like if you have your hand just kind of like palm up, kind of fingers together, kind of a straight hand starting off with. If you point your fingers in the direction of the current or in the same direction the current is going, you're then going to want to rotate your hand and curl all of your fingers in the direction of the magnetic field, and then stick your thumb out, make your thumb perpendicular to your hand. Your thumb's going to tell you the direction of that magnetic force, specifically for positive charges. For negative charges, we just know that the direction of the force is going to go the opposite way. Like there's no left-hand rule. It's just the force is just in the other direction. All right, so we're going to come up here and look at these 3 particles once again. And I'm going to figure out what direction are these particles going to end up going, and then I'm going to be able to diagram out the direction of the force on it. Okay, so I'm going to actually finish out the paths for these things. Okay, so right hand rule. If I stick my hand, so bear with me a little bit here. I'm going to try to draw something pretty horribly. Okay, so I'm going to start off. I'm going to draw my hand. 1, 2, 3, 4. That's too many fingers. Okay, I'm not an artist. All right. 1, 2, 3, 4. Okay. And rotate it so I can curl my hands up. Stick my thumb out. Yeah, I'm definitely not an artist. Okay. So really what I'm saying is the current's going that way. The magnetic field's coming towards me. So I'm going to curl my fingers, towards me. In this case, if I actually have my hand up next to the screen, pull my fingers towards me. My thumb is pointing downwards. That's going to be the direction of the force for a positive charge. So in this case, my force is actually going downward. Okay, so that means my particle is actually going to get pulled little by little, kind of down in that direction. Okay, so that means charge 2, and we said, not charge 2, particle 2, we said was uncharged. It had no charge. It was neither positive nor negative, in which case it's not a moving charge. That magnetic field won't exert a force on it it's just going to go straight. You know, at every point, it's not being deflected one way or the other. We could use process of elimination to figure out this last one, or I just know that if I apply the same right-hand rule, this way I don't have to, you know, exhibit my horrible drawing skills again. Uh, Looking at this image here, if that was the direction of the force for a positive charge, that means the force for a negative charge is simply in the opposite direction. That means little by little, actually let me start over with this one. Draw you more straight that way, okay? That means little by little, this charge is going to get drawn that way. Um, so with the magnetic field coming out at us, uh, particle 1, if it's positive, is going to be deflected downward. The negative particle, particle 3, if it's negative, will get deflected upward, all because of this right-hand rule. All right, so if I'm looking at, let me just draw a very basic magnetic field here. Once again, we're going to have the magnetic field coming out towards us. Essentially what it says is if I'm working with a positive charge, we said so long as the magnetic field's coming out of the screen towards us, and if my particle starts moving off to the right, it's going to be deflected downward. My force will be downward. And what we're going to find is that it's going to cause this circular motion, which is something we've studied before. We have a force that's always accelerating my object towards the middle of a curved path. Really what we're working with here is centripetal force. And that allows us to do some kind of unique physics things. Before we can talk about centripetal force, we needed to talk about centripetal acceleration. Because force is mass times acceleration, we kind of need an acceleration. And we learned that centripetal acceleration was just v squared over r. You know, it was the speed of the object in the circular path divided by the radius of the path it's taking. If we just take that times mass, we now have centripetal force. Well, if we have a magnetic force that's causing my charge to move in this curved path here, sorry for all the flipping back and forth, that means my magnetic force will be equal to the centripetal force, okay? So now I can set these two equations equal to each other. So I'm going to start with the centripetal force one, is equal to Q times V times B. One of the things, though, that I'm going to see here is I've got V on both sides. So if I just divide this V over, I'm going to be left with mass times velocity over radius is equal to absolute value of the charge times the strength of the magnetic field, okay? It allows me to figure out the velocity of these charges, the radius of the path it's taking, the mass of the object, um, maybe sometimes I need to know the charge on the object, or the strength of the magnetic field it's going through, okay? It lets me do a couple more physics things to kind of figure out more about the situation I'm going to be given. All right. So question 1 down there. All right. So I'm actually going to rewrite that last equation right here. So M times V, let's even just do it this way, equals Q times B. All right. So in question 1, an electron moving perpendicular to a magnetic field of 4.6 times 10 to the negative 3 teslas follows a circular path of radius 2.8 millimeters. Actually, let me start writing stuff down. So I know B is equal to 4.6 times 10 negative third teslas, or 4.6 milliteslas. And with the radius of the circular path we said was 2.8 millimeters. Once again, I can't use these equations with millimeters, so let's just go ahead and write that as 0.0028 meters. They want to know the electron speed. Okay, so that means I'm going to need to know the electron's mass and the electron's charge. Okay, and for that, is an electron is just something that we know these quantities for. So a quick Google search will tell you that the charge on an electron is 1.6. The absolute value of the charge is 1.6 times 10 to the negative 19 coulombs. And the mass of an electron is a really cool number, 9.11 times 10 to the negative 31 kilograms. Because keep in mind, when we did mass, we were working with kilograms, not grams. One of the few times that we actually don't use the base unit grams. So, or use the base metric unit. Yay, metric. All right, so really the question, once again, they want to know how fast is that electron moving. In this case, as this electron's moving through this magnetic field. So we can do this a number of ways. We can either start by plugging in numbers and then solving, getting V by itself, or we can start by just algebraically getting V by itself. So right now, if I want to get V by itself, I'm going to multiply both sides by R, because that's going to get rid of that, and I can divide both sides by mass. So now I've got velocity is equal to the absolute value of Q times the strength of the magnetic field times the radius of the path divided by mass. That is very basic algebra. I just need to plug some numbers in. So we've got 1.6 times 10 to the negative 19 coulombs, because we're just talking about one electron, times the strength of the magnetic field, we said was 4.6 times 10 to the negative 3 Teslas. Radius of the curved path, we measured to be 0.0028 meters. And we're going to take all of that and divide it by that cool number, 9.11 times 10 to the negative 31 kilograms. All right, let's see if this calculator can handle that. Do that. All right, so I've got parentheses 1.6 times 10 raised to the negative 19th, close parentheses, times open parentheses, 4.6 times 10 raised to the negative third power, close parentheses, times 0.0028 divided by parentheses 9.11 times 10 raised to the negative 31 power. Close parentheses, let's hit equals. That is a kind of a big number. So we've got, let's just call that 2.2 times 10 to the 36. Let's call that 2.2. Double check. 2.26. Okay. So the velocity of the electron is 2.26 times, whoa, that was a little weird, times 10 to the 6. Velocity, in this case, is going to be in meters per second, kind of that normal velocity we use. So that's how fast that electron's moving. Considering the speed of light, assuming this is happening in an atmosphere, is like 2.97 times 10 to the 6 meters per second. Like that's pretty close to that. Like this electron's moving super, super fast. But yeah, so that gets us through figuring out the direction of the force. If we know the direction of the charge and the direction of the magnetic field, we can kind of use our new right-hand rule to kind of figure that out. Good luck with the practice problems.